Okay, so let's take a look at this graph again. So this black curve is the drag, how the drag force changes for a steady level flight condition as a function of flight speed, and that is the graph of this equation you see here. Okay, and if you equate drag force to required thrust, let me go down. Okay, so this is what I'm talking about. So you take the drag equation and equate that to required thrust, then you can solve for flight speed from that equation. Okay, so whatever thrust required value you equate the drag force to will give you two solutions, and these solutions are given by this expression here. So in other words, this is my drag curve, and if I equate the drag to TR1, for example, that means TR1 is this level here, and if I equate the drag force to TR1 from the curve, you see that these two intersect at 2 points. One is here, the second one is here, and these two intersection points are given by this relation here. So I think if I can okay, so if I equate the drag force to TR1, then V1 will be given by here, which is the smaller solution. So that will be given by TR1 here. So let me use red color. And I put TR1 here. And there should be a negative sign because this is the smaller solution, right? And V2 will be the greater solution, right? So the V2 is going to be what you get with a plus sign here, and this V2 is the same V2 here. These two are the same V2s. Okay, so if you equate it to a different thrust required value, for example, if I equate that to, if I choose a second TR value, let me call this TR2, and this time, again, there are two solutions, and the solutions are different. Let me call these V3 and V4. And similarly, the V3 and V4 value can be obtained again from this equation by inserting TR2 instead of TR1. So I can just copy this. So instead of TR1, there should be TR2. And this should be TR2 as well. And again, for the smaller solution, I should use the negative sign. And finally, for V4, I should use the positive solution. Okay, so that's what that equation really means. Okay, so let me just go back here. So if you, the solution, that equation is obtained from here, from this equation, and if you put A, B, C here, then you get this. But if you look at here, we do a small trick here. Instead of thrust required divided by S, I write it as thrust required divided by weight times weight divided by S. So normally you can just cancel these weight terms. That's the same thing. But there's a reason why we write it as in this form. Because all these parameters are important parameters in aircraft design. And that's written somewhere here in the notes. Let me scroll down. Okay, so this one, for example, is called the thrust to weight ratio. This is a non-dimensional ratio because thrust is a force and weight is a force as well. It's a non-dimensional number, and this is a very important parameter in aircraft design, thrust to weight ratio. This ratio, weight divided by S, this is dimensional because you're dividing weight, force by an area, and that is called wing loading. And the C, D0 and K are the parameters of the drag polar. But all these parameters are very important parameters in aircraft design. So if you're designing an aircraft, then you talk about these parameters. For example, when choosing an engine, you consider your thrust to weight ratio, and you decide on what the ratio you should use based on some design requirements. So similarly, wing loading is another very important parameter. Okay, so that's why we write this equation in this form. We don't just cancel these W terms here. We specifically leave them there because this allows us to see the effect of this wing loading and thrust weight ratio on this equation. Okay. So let's take a look at the wing loading, for example. So wing loading is here. So let me. Wing loading is one of the very important design parameters of an aircraft. In this equation, we see that it has a direct effect on so I can take this wing loading out of the square root, right? I can write this as So based on above equation, we see that if we increase the wing loading, it effectively shifts the thrust required curve to the right. This is the required thrust curve. If I take this aircraft and increase the wing loading, increase this number, then the two solutions will be obtained at greater values. So how do I do that? So if I increase the wing loading, if I take this aircraft and if I increase its wing loading, then from here you will see that the two solutions, when you intersect that with constant required thrust value, will be obtained at a greater value because you multiply this solution with a greater value due to a greater wing loading. That means this thrust required curve will be shifted towards right. Okay, so that means effectively your aircraft will be able to fly faster with the same amount of thrust force. Right? Do you see that? So, do you think this is a good thing? Well, it depends. If you want to fly faster, this is a good thing, right? Because let's say with the blue aircraft, at this thrust level, you can fly at this speed. All right? And if you change the wing loading by changing the wing design, for example, then, and if you change it such that the wing loading becomes smaller, then, the wing loading becomes larger, right? If you increase the wing loading, then with the same amount of thrust force, you will be able to fly faster. So your aircraft is flying faster. And this obviously has a very important impact on flight performance. So let me just write a small note here. Same aircraft with a larger wing loading can fly faster at the same with the same thrust value. Wing loading can be increased by reducing wing surface area, right? Since wing loading is the ratio of W to S, you can make wing loading larger by making the wing surface area smaller. And here it looks that if you can do that, if you can increase the wing loading, then you can fly faster. So this is an advantage if you want to fly faster, but it becomes a disadvantage at low speed. So the blue aircraft can fly slowly, which is a good thing while landing and takeoff. So during landing, you want to be able to fly as slowly as possible, so that will allow you to land very smoothly. But if you increase the wing loading, then you won't be able to fly slowly anymore. And there's a very good example of that. If you look at this aircraft, F-104 Starfighter, this aircraft is very special in the sense that it has really small wings. So the wing loading for this aircraft is really high. Okay? So that allows this aircraft to fly really fast. So this is almost like a missile, right? It has very small wings, which is a very good thing for high-speed performance. But this aircraft has the big disadvantage that its landing speed is very high. In fact, so it has flaps. Even with the flaps, the minimum landing speed for this aircraft is about 300 kilometers per hour. So it's a very high speed for landing. And I was reading about it today before I came to the class. They say that if the flaps are broken, if the flaps don't work, then the minimum landing speed becomes, for a loaded aircraft, if its aircraft is loaded with additional like weapons, for example, there are some missiles like that. And if the flaps don't work, then the landing speed is 450 kilometers per hour. It can reach up to 450 kilometers per hour. And trying to land an aircraft at such a high speed is very, very difficult. And in fact, they say that in such a case, the pilots are recommended to just eject. Just eject out of the aircraft and let the aircraft crash, because at least the pilot will be saved. Otherwise, if you try to land an aircraft at such a high speed, it will most probably be a very bad landing, and most probably it will be a crash landing. So that's the disadvantage. Okay, so again, you see here that if you want to improve something, you have to give up on something else. And while for high-speed performance, it is a good thing to have a very high wing loading, the same thing becomes a disadvantage for landing and takeoff. Okay? Okay, so let's see what else we have. Oh, the other thing I would like to talk about is the other parameter, the thrust to weight ratio. This is also important, and you see that the thrust to weight ratio appears in this equation. But also it's important at other points as well. At other, it affects other performance, obviously. Performance specifications as well. So this is the ratio of thrust force to the weight. So if you have a large thrust weight ratio, and 1 is the critical number here. If you have a thrust weight ratio greater than 1, that means you can fly the aircraft vertically like this, right? If you are flying vertically, like in this case, your thrust force can be large enough to balance the weight of your aircraft. So let me see. Fighter jets have very large thrust weight ratios, and let me show you this video. So in this video we're going to see the F-22 aircraft taking off, and it has a thrust weight ratio of greater than 1. I remember it as 1.15 or something like that. So that allows the aircraft to climb almost vertically. So well, it can climb vertically, but in this video it's not a perfect vertical climb. But it can do a flight like that because due to having a very large thrust to weight ratio. Okay? And if you have sufficient thrust force to carry the entire weight, then you can even have the aircraft hang in the air like this, right? In fact, the same aircraft can do that as well. So let me show you this video. This is really interesting. So let me... Again, this is the F-22 aircraft. It just almost stands there, stands still for a while. So I think it's going to do it one more time. Let me see. So have you seen this maneuver before? This is called the Cobra Maneuver, and it can give you a great advantage if there's another aircraft coming after you. Suppose that another aircraft is chasing this aircraft, then if the aircraft in the front can perform this maneuver, it stays there in the air for a while, then the other aircraft will obviously pass it, right? If it cannot do the same thing, then this will be the advantage to the leading aircraft, because this time this will be in the chasing position. So the other aircraft will just pass it, and this will come back to the regular flight, and this will start chasing the other aircraft. So that gives a great advantage in dogfights, especially. So obviously for this you need a thrust weight ratio of at least 1, so greater than 1. Otherwise you cannot really hang in there for a while. But also the controllability becomes an issue as well, because while the aircraft stands still in the air, in this case none of the aerodynamic surfaces work, right? Because the aircraft is not moving, so there is no airflow around the wings. So the pilot cannot use the elevator, he cannot use the ailerons or any other things. So he has no control whatsoever. So to be able to control the aircraft in such a case, you need to have some way of changing the moments, and this aircraft uses thrust vectoring. So by thrust vectoring, what I mean is the pilot can change the direction of the thrust force. So he can make this like this, for example, if he needs to, or like this if he needs to, by changing the direction of the thrust force. So that will give him the authority to control the pitching motion, because he cannot use the elevators at all. And in this video you see how the thrust is controlled. So the pilot is demonstrating that thrust vectoring capability. So look at the engine nozzles here. So this is how he changes the direction of the thrust force. And it looks like they're connected, right? As the elevator moves, the nozzles move as well. And normally during regular flights the elevator will be providing the pitch control, but in the case of standing still in the air, then the elevator will be inoperable, and in that case the thrust vectoring will be providing the pitch control. Okay. So if you remember the crash video I showed you last week, where the Boeing 747 aircraft stalled in the air, if that aircraft had a thrust-weight ratio of greater than 1, then it wouldn't crash there, right? Because the pilot would increase the thrust force and it would be climbing. But obviously it doesn't have a thrust-to-weight ratio that large. So for most civilian aircraft, for most cargo or passenger airplanes, the thrust-to-weight ratios are on the order of 0.3, 0.35, 0.4 maximum. So they are on that order, and obviously they cannot perform such vertical flights. Okay. Do you have any questions? Okay, so I think now we can start talking about the concept of available thrust. Okay, so maybe I can just start from here. For an aircraft to maintain a steady level flight at a given altitude and speed, the thrust force produced by the engines must be equal to the aerodynamic drag force, which is called thrust required. Thrust required is determined by the flight condition and aerodynamic design of the aircraft. Okay, so the thrust required is the same thing as the drag force, and the drag force depends on the air density and the speed of the flow, or the speed of the aircraft, and I call that flight condition. And also it depends on the aerodynamic design of the aircraft, and the aerodynamic design means the CD0 and K coefficients. And thrust available is the thrust force provided by the engines, and this is strictly associated with the engine of your aircraft. So while the thrust required depends on the aerodynamic design, the available thrust only depends on the engine type. Okay? And this is controlled by the pilot. The pilot can change the thrust force produced by the engines in the cockpit through the throttle lever. So during a steady level flight, the thrust force created by the engine should be equal to the necessary thrust force, which is the drag force. So you have this equality during a steady level flight. But if the pilot increases the throttle, increases the available thrust force, then there will be such an inequality. The available thrust will be larger than the drag force. In that case, the aircraft will start accelerating. Or if he does the other, if he goes in the other direction, if he reduces the available thrust force, then the aircraft will start slowing down. Okay? Okay, now we come to our first performance calculation, which is the maximum velocity. The maximum velocity of an aircraft is obtained when the thrust force created by the engines is set to maximum, and that will give the maximum possible cruising speed for your aircraft. So intersection of the TR curve and the maximum TA curve defines the maximum velocity of the aircraft at that given altitude. And you can find that from the previous equation by inserting TA max instead of TR. Okay, so if you want to calculate the maximum speed of an aircraft, then you can find that analytically from this equation. So we were finding these flight values, and suppose that the maximum you can possibly have with this aircraft is this much. Okay, so suppose that this aircraft can have a maximum of this much of thrust force, and the maximum speed for this aircraft will be then this speed. So let me call this is TA max. Okay, so these two things are confused very often. The concept of thrust required and thrust available. Thrust required is what you need to provide to your aircraft to maintain a steady level condition, and thrust available is the actual force produced by your engines. Okay, the first one, thrust required, depends on the design of the aircraft, but the second one depends on your engine type. It has nothing to do with the design of the aircraft. If you have a certain type of engine then capable of generating a certain amount of thrust force, that is your available thrust. You can take that engine and install it to a different aircraft and it will provide the same amount of thrust force. So the thrust available is independent of the design of the aircraft. Whereas thrust required is completely dependent on the design and it doesn't depend on the engine type. Okay? And again, if you want to calculate your maximum possible flight speed, then you need to use the maximum available thrust value, and whatever that value corresponds to, as when intersected with the drag curve, will give you the maximum steady level flight speed. Okay, so this is the maximum speed the aircraft can maintain a steady level flight. It can reach higher speeds momentarily while, for example, diving, but if you are talking about a steady level flight, then the maximum possible speed will be given by this point. Okay? Okay, so now after talking about the available thrust, it's a good point to talk about different engine types and engine characteristics. So we have 10 minutes left, so I think we can start talking about that topic. A propulsion system, which is actually the engine, so the engines are called propulsion units. A propulsion system is a machine that produces thrust to push an aircraft forward. And thrust is usually, well, I shouldn't really use usually. Thrust is always generated through application of Newton's laws of motion. Air is accelerated by the engine, and the reaction to this acceleration produces a force on the engine. Okay, so you have air here. The engine sucks in air and then gives air an acceleration. Okay, so normally the air is stationary. The engine sucks that air in and then pushes out with some velocity. Okay, and this is possible by applying a force on the air, right? The engine takes air in and then accelerates it by applying a force. So the Newton's second law of motion is in action in that case, there. And as a reaction, the same amount of force is applied by the air on the engine. And that reaction force is what forms the thrust force. Okay, so now there's an important point here that I would like to talk about in regards to the efficiency of aircraft engines. So let's take, I guess before the equations, it may make sense to talk about this. Okay, so the engine takes air in and pushes it backwards, right? The engine pushes air back, and the air pushes engine forward, and that is the thrust force. Let's see how to tell this. So air, we don't see air, right? So it's really difficult to understand this on air. So instead of talking about air, let's take a look at another example which the same concept is applied, but it is easier to visualize and easier to understand. Okay, so let's take a look at two persons, right? So suppose that these persons are on ice. They have ice skates, so there's no friction. And suppose that this person pushes the other person, okay? And as they push each other, since there's no friction, they will both start moving, right? And this person will be moving, will give himself a push, so he will start moving with a certain speed, and the other person will be moving at in the opposite direction with, again, a certain speed. And this person, suppose that this person did the pushing, so his goal was to accelerate himself, right? So he's pushing the other person to accelerate himself. But since the other person starts moving as well, you can say that the effort this person put into accelerating himself is divided into two, okay? And some part of it becomes a useful work for this person because he starts moving, but some part of it is spent on accelerating the other person. And this part of the energy that goes into accelerating the other person is a loss for this person, right? Because his goal is to accelerate himself. He doesn't care about what the other person does. But he's putting in that effort. So a part of his effort is turns into energy for the other person, which is a loss for this guy. Okay? So it would be much better if he could push himself against the wall, right? So instead of pushing against another person who's free to move, if he could apply the same amount of push against the wall, with the same effort, he would gain a larger velocity, right? So this is obvious, right? Do you have any? Can you follow? So this is really important to understand because this is the source of efficiency, engine efficiency. So once again, suppose that you are on ice with ice skates, and if you push yourself as hard as you can against the wall, then you can give yourself energy, right? You can gain a certain speed out of that. But if you do that against another person who is free to move, then you won't gain the same amount of velocity. That's because some part of your energy will go into accelerating the other person, which you don't care and which is a loss for you. Okay, so there's another example trying to explain the same thing again. So this example is the same as the previous example. In this case, I'm using this example. Suppose instead of pushing against something on ice, this time let's consider this person climbing through a rope. Okay? In fact, I have a video of that. Okay, so this person is putting in some effort, and his effort turns into useful work for himself, right? He accelerates himself and he climbs. So he increases both kinetic and potential energies for himself. And his muscle power is doing that for this person. So imagine that guy was doing the same effort in this form. So instead of climbing on a wall which is fixed to the ceiling, if it was attached to another mass through a pulley like this, with the same amount of pulling, he would be raising this mass here instead of raising himself up, right? So he would be spending pretty much the same amount of muscle power, but that power, instead of turning into useful work for himself, it would be turning into useful work for this mass. Okay? And he would be spending the same effort, he would be getting tired by the same amount, but instead of going up, he would be lifting this mass up. And unless his main objective was to raise this mass, then you can say that the energy that goes into this mass is a loss for this person. Suppose that the person's goal was to increase his own energy, but if in this case he can do that, he can increase his own energy to increase he uses his own muscle power to increase his own energy by increasing his kinetic and potential energies. But in this case, the same effort goes into increasing the energy for this mass, and that becomes a loss for that person. Okay? So the same analogy can be applied here. The aircraft engine, the purpose is to generate a forward force on the engine, but the air that is ejected out of the engine with a certain energy, with a certain kinetic energy, is really a loss for the engine, right? The engine, the main objective of the engine is to generate a forward thrust force, and the energy added to the air as it leaves out the engine with a certain speed is a waste for the aircraft engine. Okay? For example, if the objective was to accelerate the air, for example, if you are designing a fan to blow air, then you wouldn't call that a waste, because your goal is there to accelerate air. You want air to flow. In that case, obviously, that's not a wasted energy. But if you're talking about an aircraft engine, then the energy of the exiting air is a loss, and that determines the efficiency of a propulsion system. Okay? So our time is up, so let me stop here. And this determines the efficiencies of different types of engine. In this course, I will be talking about the jet engine and the propeller, the thrust force obtained by a propeller. Then these two are have different efficiency levels, and I will be talking about that on Friday. Okay? So let's stop here.